Okay, so what I want to do today is I want to start by giving people the opportunity to ask about homework questions. And then when you get your homework back tomorrow, we'll talk a little bit about like what the procedure for that is going to look like, because I have told the grader to be particularly nitpicky. But I'm also going to allow you to revise anything in here, and most of the revisions are going to be trivial to get all the points back, right? So my approach to this is to try, I'm going to grade you on the homework in a way that probably seems overly intense in terms of what I'm focusing on, but it's because I'm trying to prepare you for proof classes that come after this one. And I really want the focus to be on telling you the truth about what you're doing, but also giving you the opportunity to completely revise. Most of the time, they won't be major revisions for like full credit, right? So the homework is split up into some credit that you're getting for doing the work. Half of the credit on every homework assignment is, did you do all the questions? And the other half is, how did you do on one or two of those questions? Okay, so you can yell at me tomorrow when I hand these things back, but the idea is to tell you exactly how you did on these things, and then have you hopefully, like, I want everyone to get full credit on everything if they can, so to encourage you to revise stuff. So we're building the foundation for what comes after this. All right. So are there questions I can answer about things that showed up in the homework? Yes, you just have to cite it, right? That's one of those things where you can just point out like, hey, basically anything that we're passed in the book, at any point, anything that we're passed, you can use if you cite. You just have to tell me what you use. Right, but yeah, you can do that, of course.
So number one, in general, not just like specific, how would you go about moving the
Which was 2A number one?
So if you want to before span B,
B span B, and this one was like B1, comma B2,
B1 minus B2.
Okay. So one way to be able to do this would be able to exhibit a specific, so if you're going to show that something is in the span, right? If I want to show, so what we're trying to do here is say, if B span B, then this set also spans B. Right, that's the exercise. So the idea is, if you are ever asked to show that something spans a vector space, you have to show that an arbitrary element in this space can be written as a uniform, as a scalar, a linear combination of these vectors, right? So basically, any sort of argument about spanning set is going to boil down to if V is in V, then V equals, say, C1 V plus C2 V1 plus C2 V1 minus V2 plus C3 V2 minus V3 plus C4 V3 minus V4.
I think it's not V1. Like it's taking off V1 and then add V4.
Oh, okay. I mean, the argument will be it's the same exact idea, right? I mean, the argument's different, but here, let me fix it so that it's correct to the book. If V is in V, so basically, if you were to formally write this, what you would write is, we will show that if V is in V, then there exists a C1, a C2, a C3, and a C4, so that V is equal to C1 times V1 minus V2 plus C2 times V2 minus V3 plus C3 times V3 minus V4 plus C4 V4. That's really your first step. What are you going to prove to me? You're going to prove to me that an arbitrary V can be written as a linear combination of these guys. What that means really is you have to tell me what the C1, C2, C3, and C4 are. It's not enough just to say, oh, well, obviously, because it's a linear combination of V1, V2, V3, and V4. You have to tell me what the scalars are, right? So the next step in this argument is say, well, where am I going to get a C1, C2, C3, and C4? What information do I have to work with? Well, I have this information, right? I know that V, so because V1 up to V4 spans V, there do exist an A1, A2, A3, and A4, so that V is equal to A1, V1, plus A2, V2, plus A3, V3, plus A4, V4. And now the idea is, can I use the fact that I know this to figure out what C1, C2, C3, and C4 have to be, right? This has to exist because V is in the span of those four vectors. I don't know that this is true unless I can tell me the C1, C2, C3, and C4 that actually do it. The thing is, you can work backwards from this to figure out what C1, C2, C3, and C4 must have been in terms of A1, A2, A3, and A4. I know this is true because of that. So if this were to be true, if V was equal to this, then also V would be equal to C1 V1 minus C1 V2 plus C2 V2 minus C2 V3 plus C3 V3 minus C3 V4 plus C4 V4, right? That would have to be true. Okay, collect like terms here. Make it look like this. V is equal to, I guess there's just a single V1, C1 V1, and then we've got a plus negative C1 plus C2 V2, and a minus C2 plus C3 V3, and a minus C3 plus C4 V4. What does C1 have to be? Like if I want to show that this equation holds for some selection of C1, C2, C3, and C4, but I already have V expressed like this, could I find a C1 that would make this work? Well, yeah, if C1 was A1, that would be a good start. What I'm going to try to do is I'm going to try to pick C1, C2, C3, and C4 so I just get these values back again because I already know these add to V. So what I'm going to say is, oh, well, if C1 was equal to A1 and C1 minus C1 plus C2 was equal to A2 and minus C2 plus C3 was equal to A3 and minus C3 plus C4 was equal to A4. If I could figure out the values that made this system of equations true, I'd be done. This linear combination would be the same as that one. I already know that as a. So the point of the game is, can you find the scalars that make this pile of equation turn into this pile, which I already know is equal to B? All right. Actually, what are they? Like, let's see. Can we solve this? C1 is A1. If minus C1 plus C2 is supposed to, again, remember, A1, A2, A3, and A4 are known numbers at this point. We know those numbers. They are known quantities. Yep.
Do we have to continue this or are we okay?
Well, in principle, you like if you were an exam or something like that and I asked you this question, you could say, yeah, just solve the set of equations and there you go, right? But how do you know this is a consistent set of equations and this is actually solve it? There's all kinds of linear systems like this that have no answer, right? And if you tried this and you got no answer, then you wouldn't have it. So I guess, you know, from the standpoint of exactitude, one might say that it would be a good idea to tell me precisely what the C's have to be. I mean, it's not so bad because if minus C1 plus C2 is equal to A2, but C1 is A1, then that means that C2 would just be equal to A1 plus A2. Now you've told me what C2 is. If I want to know what C3 is, I have to solve this equation. Minus C2 plus C3 is equal to A3, but I know what C2 is. Minus A1 plus A2 plus C3 is equal to A3. Now there's only one unknown in the equation, it's C3. So C3 must be equal to A1 plus, I'm starting to see a pattern here. And likewise, if you solve the last equation, well, the last equation says that minus C3 plus C4 must be A4. Minus C3 plus C4 is equal to A4. Well, that's going to imply that C4 must be A1 plus A2 plus A3 plus A4. Now you've given me exactly the coefficients in terms of known quantities. If you take these four coefficients and you put them into this equation, you're going to get V back again. So you've exhibited that an arbitrary V can be written with these numbers that I already know exist to give me feedback. All right. Okay, I know it's just linear. It's just algebra. There's an algebra in linear algebra. And it's linear, they're all lines. Okay, does that answer your question? I mean, they're not all going to be like this, where there's a lot of work to find the A1s and A2s. But from a standpoint of theme, the idea of using something that we know to show that something we don't know exists, that's a pretty standard sort of setup for problems like this, right? So my approach to it was write down what the question was, and then work backwards to figure out from known information how to solve the unknown question. Anything else? All right.
The two A's for part A, when it says B is not equal to 0, are we looking at the vectors?
That's going to be a vector. Yeah. Okay. Remember that I have office hours tomorrow, 2 to 3. And also, if you guys are wandering around the math building for whatever reason and my door is open, you're always welcome to come bother me. Right? If my door is open and you walk by and I'm in there, just you can ask. I like talking to students, and I know some people can't make the main office hours. Okay, so if there's no more homework questions for the moment, let's finish up what we were talking about last time. So we were finishing up the theorem that said that you could throw out a vector and keep the same span. So we were proving something called the linear dependence lemma. And the point of the linear dependence lemma was that if you suppose that you have a V1 up to Vn as a linearly dependent list, and then the idea was that you could find some index. There exists an index J, so that Vj is in the span of everything that came before. That's conclusion 1. And conclusion 2 was that you could take Vj out of the list and keep the same span. Removing Vj from the list doesn't change the span. And we sort of got an, I would say an argument, but a conversation about the sort of algorithmic approach that Axler takes, right? The key idea of the proof was the idea that because you know this list is I mean, basically what you do is you write down this equation. So since, I'm going to go through this a little bit faster this time. Since V1 up to Vn is linearly dependent, and everybody in here right now, think about what that means, because you should be able to write down the equation and the condition if I say linearly dependent. So I'll give you the equation this time. So to say that a list is linearly dependent is to say that this equation equals 0, and what's the condition on the coefficients? At least one of them is not 0. This is dependent, not independent, right? I make this mistake regularly as well. So yeah, so to be linearly dependent means that as a way to assemble up a 0, but without having all the coefficients be 0. Yep. I'm mixing these together. N and oh yeah, N. Sorry, it's N. Thanks for asking. Okay, and not all of the of these, of the AK here, not all of the AIs are 0. So something in this list of coefficients is not 0. So what we said was thinking of the list, so thinking of the index list. So there's this index set that goes from 1 up to j, and then it goes all the way up to n. And what we said at the end was we're going to pick the largest index that corresponds to a non-zero value of a, right? So if the 10th thing in the coefficient list was the last one that was the last one that wasn't 0, we would pick a10. The idea here is when I sort these coefficients out into a list, I'm going to choose the one farthest to the right that is a non-zero element. So I select the largest j, contained in the index set 1 to n, so that aj, I'm not writing hard, so that aj, so that aj is not 0. That means that I could write, so then I write this. A1 V1 plus A2 V2 plus AJ minus 1 VJ minus 1 plus AJ VJ is equal to 0. I could write that down because everything that came after AJ was 0, remember? So I've cut the end of this sum off because everything that came after AJ was a 0. Those terms aren't there. So now I'm just going to put this on the other side of the equation and divide by AJ. What justifies dividing by AJ? It's not 0. I can divide by it. Okay, so BJ is equal to minus A1 over AJ V1 minus A2 over AJ V2 out to minus AJ minus 1 over AJ VJ minus 1. And that says that Vj is in the span of V1 through Vj minus 1, right? I've written Vj as a linear combination of everything that came prior. So Vj is in the span of V1 to Vj minus 1. I've exhibited as a linear combination of vectors V1 through Vj minus 1. Right? Now, what that means is, this is also, because Vj is the span of everything that came prior, I can throw it away without changing the span of the vector, without changing, I can get rid of Vj. It's not contributing anything to the span, right? Because it's the span of everything that came before it. It's adding no new directions, right? Vj has no new information because anything that Vj could be adding to a linear combination, V1 through Vj minus 1 are already providing. Also, span of V1 up to Vj is equal to the span of V1 up to Vj minus 1. Because Vj was in this span. Yep. It does not imply that it's linearly necessarily. I mean, no, because we picked the largest non-zero vector. There could still be independence relations that we haven't got. So if you want to think about algorithmic, this actually concludes the proof, right? And if you want to think algorithmically about how you might apply this over and over again to take a linearly dependent set and turn it into a linearly independent one, you just apply this repeatedly until you don't have a linearly independent set of vectors anymore.
But what if like there's some zeros trapped in the middle of that?
You're going to work from the right and then go, like each time you go, if you applied it again,
Or
you just
knocking
keep
off the last
moving. Yeah,
one?
you keep moving off the last one, right? Until you no longer have a linearly independent set. That's the idea, is that eventually what will happen is you keep throwing vectors away, you're eventually going to lose all of the dependence relations, and what will be left, the only way to make that equation equal to 0 will be put zeros in everywhere, right? So this does not necessarily guarantee that this big span, or that this list of vectors suddenly becomes linearly dependent, but we're going to see that it means eventually you can make a linearly independent set out of a linearly dependent one. You guys did this in 206 when you row reduced a matrix and found columns of zeros and just got rid of those columns. The same exact idea in the theory here, but we're not referring to matrices. Okay. So basically the operation we're doing here is the same as row reducing a matrix, finding the zero columns and throwing the zero columns away from the original set. Yep.
Why do we have to take those? You're just like, forget everything.
What? Well, there's a concept called mathematical maturity, which exists in math education that says you're supposed to have seen stuff at the computational level before you see it at the theoretical level. The larger answer is that like 206 is for engineers and scientists, and 306 is for mathematicians. Right? That's really it. I mean, the basic ideas in that class are pretty similar. Okay, so that was that one. So basically, the upshot of the linear dependence lemma is that given a linearly independent set, given a linearly dependent set, you can always find an extra vector that can be removed without changing the span. So in some sense, what we mean by a linearly dependent set of vectors is there are too many vectors inside there. There's extraneous information coming in from vectors. We don't need to make linear combinations. Okay, now, as our application of this idea, we're going to prove a theorem that on its face looks kind of weird. And boy, oh boy, is it a good test of how well you know the definitions in this class. I'm gonna get chalk out. I'm gonna highlight every definition that you're supposed to know in this one. Okay, in a finite dimensional vector space. So already we've got two. Here's one. Here's one. The length of any linearly independent set list, linearly independent list. There's another one. Linearly independent list is smaller, I'm sorry, is less than or equal to the length of any spanning set for V. This is what these theorems end up turning into, is giant piles of definitions all thrown together. In a finite dimensional vector space V, the length of any linearly dependent list is less than or equal to the length of any spanning set for V. So if I spun my random arrow and I picked people out in the class, one by one, I asked people what all these definitions meant. What does it mean to be finite dimensional? Don't all rush to volunteer here.
The span can be represented by
Of vectors in the space. All right, cool. That's finite dimensional. What's a vector space?
Those 6 properties.
6 properties that make algebra consistent, right? Which basically boil down to closure under addition, closure under scalar multiplication, and basic algebra. Yep. Yes. You got to have your definitions down. What does it mean to be linearly independent? I mean, I am emphasizing this over and over again, not because, I mean, to really encourage you to remember the definitions. There will be definition questions on the exam.
And that the scalars are
Is the only answer to the equation. right? So it's not just enough that A1 through AN is equal to 0. It's the only way that you can make that equation equal to 0 is A1. Very nice. Okay, spanning set. Spanning set for V is a set that does what, or a list that does what? Yep. Beautiful. Yeah, every V and V can be written as a linear combination of elements in the spanning list. Beautiful. Okay, you got to have all those basically. I'm going to try to continually remind you, like you can tell we're already accumulating all this stuff, right? This is like piling up on top of itself, especially because these definitions are built in terms of each other. Okay, it's important that you stay on top of your definitions. And I'm mostly emphasizing this because I'm just trying to point out that like the theorems actually start to become incomprehensible unless you understand what they're referring to. If you don't know these definitions, this just looks like a pile. It might as well be a magic spell, right? I don't know, linearly independent something. There's some vectors. Well, these things aren't true in infinite dimensions. So we basically have to throw away the possibility that we have infinitely long lists, because with infinitely long lists, you have to take care about things like adding a finite list of vectors always makes sense. You guys spend a lot of time in your calculus classes talking about when it makes sense to add an infinite number of things together, right? The sequences and series section of calculus is all about when adding an infinite list makes sense, right? We don't want to deal with that in here. That's a higher version of linear algebra, is the mix of linear algebra and calculus. But you need all this calculus stuff to talk about infinite dimensional vector spaces. So we're just restricting ourselves to things where we know adding always makes sense. Okay. This has an argument that I find, I actually find this argument kind of dissatisfactory. I'm going to show you how it works, like what Axler's argument for this is. I mean, I believe it, it's nice, but it's not very, you have to think your way around it a little bit, right? Because I mean, this is kind of a weird theorem. If I have any list of linearly independent vectors, it's always smaller or less than or equal to the length of any list of a spanning set is an odd way to phrase the theorem. So that the proof is sort of oddly phrased too. So we're going to start by, we're going to suppose that V1 up to Vm is linearly independent list. And we're going to suppose that W1 up to Wn, these are different, M and N. W1 to Wn is a spanning set. For V. Okay, those are our pieces. Yep.
Spanning set doesn't imply that they're linear.
It does not imply that they're linearly dependent. So just as an example to keep in mind, that spans R2 or C2, right? That's a spanning set, but it's not linearly independent because this is the sum of these. So spanning set could have extra vectors inside of it as long as it covers everything. So this set spans R2. On the other hand, this set 1, 0, 0, 0, 0, 1, this is a linearly independent set, but it doesn't span R3 because I can't get vectors that have a 1 in the origin here. So linear independence and spanning are not the same behavior. They're not related to each other. Okay? Separate properties. And that's what makes this theorem so weird, right? Is that there is a relationship between linear independence and span, the idea of a spanning set. Okay, so the proof of this is another one of these stepwise algorithm sort of arguments. So basically, he's going to do the following. He says, okay, what we want to show. In fact, I'll put this in a different colored chalk so we have it. So if I have a list V1 through Vm that's linearly independent, and a list W1 through Wn that's a spanning set, what I want to show here is that M is less than or equal to N, right? M is the length of the linearly independent list. N is the length of the spanning set. I want to show that M is less or equal to N. These were arbitrary. So if I can just show, like picking an arbitrary linearly independent set and an arbitrary spanning set that M is less than or equal to N, I'll have proved the theorem. I encourage you to read this argument as well. Okay, so here's what we're going to do. We're going to start by we're going to be operating on this object B. So we're going to sort of initialize B by letting it be equal to the list W1 up to Wn. So we start by letting B equal to all the W vectors. Okay, now, and by the way, V, we should point out here that the span of the list B is the whole vector space, right? I mean, that's the whole point of V1 through Wn, W1 through Wn being a spanning set, is that its span is the whole space, yeah? Okay, now put one more vector into the file. We're gonna take V1 and throw it into the list. So now extend B to be B equals V1 W1 up to Wn. So I'm going to take V1, I'm going to put it on the front of the list. Yep.
So the list of B and W they both live in the same.
These are all inside of a vector space B.
Okay.
Yep. I'm going to make an assertion, which is that this is a linearly dependent set. Why is it linearly dependent? How do I know that? Without any other information, I'm going to say that's linearly dependent. Why? Oh, yeah. Which means that any other vector could be written in terms of these, right? Okay, so automatically this must be in B. B is spanned by these. So V1 must be a combination of these vectors. It has to be, right? I mean, it's in B, so it must be in the span of W1 through Wn. So that means that that new set B that we have, here's what we did so far. We started with B, which was W1 to Wn. Then we made B into V1 W1 up to Wn. The span of B, I haven't changed the span, it's still V because I can't leave the space. This is linear, now B is linearly dependent. It has to be because B was in the span of the W, right? B1 is in the span of W. Now, that means somewhere out here, there's a vector I can get rid of. Because that's what the linear dependence lemma says, right? The linear dependence lemma says, oh, if a set of vectors is linearly dependent, I can throw one of them away without changing the span. So one of these W vectors can be gotten rid of. The idea here is somewhere out here, there's a W that is equal to the span of everything that came before. By the linear dependence lemma, there exists a Wj in the span of V1 up to everything that came before, Wj minus 1, say. And I can get rid of that vector without changing the span. That makes sense? I've identified something up here that is now a linear combination of everything that came before, and I'm going to throw it away. Throw it away. Well, throwing it away means now I've got a new list. B is equal to V1, W1, W2. We get up to Wj minus 1, but then we skip to Wj plus 1, and we keep going to the end of the list. That's what the linear dependence lemma lets us do. Find a vector up here that's in the span of the previous, throw it away without changing the span. Span of B still equal to B. Okay, now all I gotta do now is just turn the crank. I'm gonna do this over and over again. What do I do for the next step? Now take that list and add V2 to the front of it. Now add V2. Now B is equal to V2, V1, W1 up to Wn, but where I've deleted Vj. Vj is already gone from the process, right? Wj, sorry. So right now we're just missing Wj from step 1. Now that set has to be linearly dependent. Why does it have to be linearly dependent? Because the span of this was all of V, and so any other vector in V can be written as a linear combination of these guys. So this is linearly dependent. Now I'm going to, yep. We are pulling the V, so we're going to use that fact right now. It can't, V1 might be involved here, right? But so what's going to happen is we're going to say, now I want to throw another, this is linear dependent. I'm going to invoke the linear dependence lemma again to throw away another vector. But Y doesn't have to be V1. How do I know that there's no relationship between V1 and V2? Because they were linearly independent vectors, right? So wherever the vector I throw away is, it must be out here somewhere because those are independent. V1 cannot be in the span of V1 and V2. Can't be. Okay, so then we're just going to sort of rinse and repeat, right? Throw away. So there must exist one of the W, I'm going to call it Wj hat or something. There's a Wj hat that is in the span of the previous vectors. So throw it away. And the resulting list looks like V is equal to V2, V1, W1, blah, 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 V, and where now I've thrown away 2 of the W vectors. Why am I allowed to keep doing this? Because the point we're going to do here is we're going to say, do this over and over and over again until you run out of linearly independent vectors. Why are we sure that there's always going to be enough W's to make this happen? Well, then we have to conclude, we want to conclude that n is bigger than m. So I can only conclude that the V list, the W list was bigger than the V list if I can say I can run this process all the way through. Yep.
So since the V's are linearly dependent,
Independent.
Sorry, the vectors that we're kicking out are the vectors that are already man.
You got it. I mean, you have the idea.
Dependent on V1. So if a V1 is already in there, then that means that any missing one is already kind of held by that.
Yeah. Okay. So you've got absolutely the right idea, right? That like because the vectors that you're piling into the front are linearly independent, and the linear dependence lemma says, and every single time you add a vector, it will always be linearly dependent because the span doesn't change. You're putting more vectors in, but the span doesn't change. But you can never kick out one of the V's because they're linearly independent. So the linear dependence lemma says you've got to kick something out. Well, where must it come from? It must come from the W side of the list. And so the W list must be bigger than the V list, and that lets you conclude the argument. I don't know if you understand what I mean by saying that this is sort of an unsatisfactory argument, but I did that. I was like, okay, I mean, basically Axel at this point says, turn the crank. You're always going to have a W to throw away by the linear dependence lemma. So you just do this n times, or sorry, do this m times. Each time it will be possible by the linear dependence lemma. Each time the step is valid by the linear dependence lemma. And you will never be able to throw away a V because the V's are linearly independent. So there must have been enough W's to make this possible. And then therefore m is less than or equal to n. Therefore, m is less than or equal to n. And so that's basically what the algorithm is. So I encourage you to read this argument until you understand what the heck he's trying to do here, right? But the basic idea is he's saying every time you add, it's linearly dependent. So there must be something you can remove because we proved the linear dependence lemma. It can't be a V, so there must have been enough W's to throw another one away. That's the basis for the whole argument. Yep.
Like proof-wise, is this proof won't say valid, but
So,
because normally we do induction.
yeah,
and we
this
have
is
to
not
do
an
it
inductive
here.
argument. This is what's called, this is a type of argument called a terminating algorithm. So this is a terminating algorithm. It describes a process. It's essentially, it's basically like a finite induction, right? He's saying every single step is legal to take. And eventually the process stops because I run out of linearly independent vectors. So the process, every step is valid and it stops eventually because I run out of inputs. And so that's what makes it a valid argument. So it's very much akin to induction, but we don't have to show it for all integers. It's like a finite version of induction.
So we stated earlier that the span doesn't change, and that's by the. Okay.
Yeah, the span doesn't change by the linear dependence lemma.
So then how can you like do it? Oh wait, m times. Okay. so
Yeah,
you couldn't do
m
times.
times, not n, right? Because remember, what the linear dependence lemma says, anytime you construct a linearly dependent set, you can always remove something, right?
So the length of like this list at the end of this algorithm will be like.
It's still
m.
length n. It's still length n. It's the m vectors you piled in from the linear dependent set plus whatever was left over from W that you didn't kick out.
Okay.
The overall length of the list never changes. Is the idea. So the list M can live inside the list after you boot things out. Yep. Actually, yes. You're gonna this sort of like algorithmic approach is going to be also the way that you describe constructing a basis from a linear dependent set as well. Yep.
Are we guaranteeing the length of the list doesn't change, or just the span doesn't change?
We're not, so in the argument, the length doesn't change, but like here, really it's the span. It's that the span doesn't change is what drives the whole thing. Since the span never changes, every vector I pile in is in the span of everything that came before, so that forces it to be linearly dependent. At every step, we're guaranteed the step we construct is linearly dependent, which means we're guaranteed to be able to remove a vector from the list. So we absolutely need the linear dependence limit for this argument to be valid. Yep.
How do you know that like you wouldn't like run out of W vectors and you'll just be like adding new vectors?
Well, because the linear dependence limit says anytime you have a linearly dependent, this is where the logic is like a little strange, right? Because the linear dependence limit just holds. It says anytime you have a linearly dependent set list, you can always remove a vector without changing the span, right? What this is saying is, well, every step there was a linearly dependent set. It would be if I ran out of W's, it would mean I had a linearly dependent set I couldn't remove a vector from, but that would be a contradiction of the linear dependence lemma. So we can't run out of W's. We must be able to run all the way through the end. Yep. Because we assumed the V's were linearly independent. And the way we look at this is we say, okay, whatever the linear dependence lemma says, go down the list until we find something we can kick out, right? But these guys can never be kicked out because they're not in the span of each other, right? They can't be. They're linearly independent. I can't write V1 as every vector I pile in from the V's can't be written in terms of the other V's. It's a linearly independent list. That's why we have to use the W's to kick vectors out and not the V's.
Even though there's a ton of non-V in the set.
That's right, because of the way we've rigged this whole thing up is that we're always sort of saying, okay, can I kick a vector here out? No. Can I kick it? Well, now all of a sudden I've got vectors I can start kicking out and I slide my frame this way until I find the largest of those, right? So the beginning of the list is set up to make sure, that's why we set it up the way we did, is that we look down the list this way and say, is that in the span of the previous? No. Is that in the span of the previous? Well, no, because the V's are linearly dependent. That might be, but if it was, the vector we kick out would be that one. Yep.
And we do this n time because we have n number of v.
Yeah, we had m V's, so we have m inputs. I have to be able to run this m times.
And then the set of the w eventually will run out because the set is
Well, the W's won't
finite.
run out. It means that once we've gotten past all of the what 1 through m, then the process stops, right? I'll have to plug every single linearly independent vector into the front of the list, and then there's no more to do. Just the process just quits. So now, how does this show up in your homework exercises? In the 5 minutes I have here. Okay. So the idea of this argument is that we can use this to establish when sets of vectors can even be a spanning set or a linearly dependent set. A problem that came up on the exercises was something like, show that no set of 4 polynomials can span P4. It was one of the exercises, I believe, right? Can a set of 4 polynomials span Pf4? And the answer is no. And the reason is I can find a list of 5 linearly independent vectors in P4. This set, 1, z, z squared, z cubed, z to the 4th, I hope you believe me that these are linearly independent, right? The only way to get these to add up to 0 is to put zeros in front of all of them, right? If you, I mean, this is the linearly independent set. The only way to write C1 plus, or sorry, A naught plus A1z plus A2z squared plus A3 z to the 3rd plus A4 z to the 4th is equal to 0 is if they're all 0. The only polynomial that's equal to 0 is when all the coefficients are 0, right? How many vectors are in this linear independent list? 5. So how many vectors must be in any spanning set for P4? At least 5. At least 5, because the size of a spanning set must always be larger than the size of a linearly independent set. So since I found a 5-vector linearly independent set, any spanning set is going to be at least that big, because every linearly independent set is less than or equal to in size any spanning set. Yeah.
When you set it up like that.
Yeah.
Well, obviously.
I mean, basically the idea is that if you're in PM, no set of length less than m plus 1 can possibly span PM, because there's you can write this list down and it will be linearly independent. Okay. And this is, now you should imagine here, you might suspect if you know that, like the idea of a basis, you should imagine that basis is lurking around in the background of this, right? Because we've already mentioned that linear independent sets and spanning sets don't really mean the same thing. But yet there's this weird boundary between them where if I have a linearly independent set of size m, it must be less than or equal to n. This is linearly independent. And this is a spanning set. But what happens if they're actually equal to each other? Is it possible for them to be equal? If they were equal, it would mean something could be linearly independent and a spanning set at the same time. And that's what we're going to define to be a basis, actually. It's a set that's both a linearly independent set and a spanning set for a vector space. Okay. So these two notions that are not really related come together in the notion of a basis for a vector space. Okay. All right, so I will release you. Thanks for putting up with this argument. Not my favorite. I encourage you to read it to get your mind around what's going on. Axler loves these algorithmic descriptions of how you attack the proof of a theorem. So it won't be the last time we see an algorithm like this, okay? Okay. What are you saying about that? Find the vector zero. Can it be 2? No. Can it be 1? No. You're like W1, well, sure, wherever it is now, it's going to be somewhere in this part of the line, right? Okay, so do it. Then put B3 at B3. Could it be B3? No. Could it be B2? No. So the next one to throw away, which has to exist, must also come from this part of the way. And at every step, you must be able to throw something away, because this is guaranteed to be linearly independent. And so since you have to throw something away and it can't come from here, it must have come from here, which means there always must be enough stuff here so you can keep throwing things away.
Oh, thank you. How do you late? I can't attach it on there.
Go ahead and send me, if you send me an email, I'll send you the class. Okay. That's encoded in like, I think that's on my permissions page. Like I don't think you can, I'm not sure where it is in the catalog.
Thank you.
Yep.
This was like number 20 on the homework. So I was like trying to find like where U was like an answer. Like a W, so
That would work. Yeah, what you got. Yep.
Okay. Okay. Just checking.
Yep, this is right, because you just need to be able to adjust to things right here. Then it's just up to you to show that thing you work there as a subspace and also the subspace.
Yeah, it was. I started thinking it was like it's like R4.
Yeah. So the idea, I mean, the basic idea is that what you want to say is, if you wrote down some arbitrary vector, And you know you could write this one. In your case, actually, you wrote this. YY, WW. This one is in U, right?
Yeah, that's you.
And then what you said is, oh, okay, well, to get this to be not a W, you have to add something in this. So you would want to do Z minus W, because now W plus Z minus W is Z, right? And then you said, okay, well, to get an X here instead of a Y, we have to do Y. So you didn't do this by telling you this is the thought process. Is you've adjusted the first slot to make sure you get something different up here. You set the third slot to get something down here.
And
So
all
I think
my
on your
older
sheet, you've
degrees
got written it's this, it's just this, you did this. This is the same thing you did. This is one way of figuring out what it must be, what this object must be. So vectors that look like X, Y, Y, that's U, and vectors that look like S0, T0. That's enough to make a direct sum here, which is what you got on your page. It's literally the same thing.
Okay. Yeah, I guess I was wondering, it's like hard for me to like calculate. It was kind of like a guess and check, I guess, but not.
I mean, but that's the idea is like what you should be thinking is, okay, if you had this vector, what's the closest you could get using something of the form X, X, Y, Y? You might think, well, I don't know, I could write 2, 2, 6, 6, that's pretty close, at least it matches in these two spots. How do you adjust that to make the other parts of it work? Because this is all of F4. This is from U. So what would I need to add on here? Well, I have to put a 1 right here. And then also I need a 3.
There's like the minimum amount you need.
Yeah, exactly. Exactly. It is the minimum amount. So that's actually sort of your guess and check is the right intuition, which is you have to be working with linear combinations of these guys in order to fix this. Right? And so the set that you got is just.
Because I was looking at one of the solutions and it was almost like more complicated. It had like S, negative S, T, negative T, and I was like,
There's an infinite number of solutions.
like why? Yeah.
Yep.
Okay. So that's what I was just like making sure. I was like, I think this is simple.